Today I'd like to give you a rather dramatic example of what happens when data types go wrong. This is the Ariane 5 rocket. It was designed and built by the European Space Agency and launched from their facility in French Guiana, which is in the northern part of South America. And, well, I'll just let you watch it, and we'll see. Rocket explosions happen all the time. You can find SpaceX ones relatively recent. This one happened a few years ago, but I'll play you some of the YouTube for this particular rocket, and we'll see how it went.
By the early hours of the morning of the 4th of June, Ariane 5 stood proudly on ELA 3, waiting for the final countdown. No one would sleep much that night. They never did before any launch. The skies opened again, and the tropical rain poured down over the rocket. There were doubts if it would be able to launch the next day. Its prospects looked poor. By the next morning, the forecast had improved slightly. A final decision to go was taken.
10, 9, 8, 7, 6, 5, 4, 3, 2, unité, feu. Allumage. Décollage.
Everything looks fine here until something strange happens. Keep your eye on the rocket. There's a course correction here.
Tous les paramètres propulsifs sont normaux et la trajectoire est normale.
37 seconds into the launch, the onboard computers decided 501 was 90 degrees off course.
Bummer.
They made an automatic adjustment to the trajectory as the rocket was traveling at the speed of sound. A well-rehearsed civil defense evacuation began immediately as clouds of toxic fumes enveloped the surrounding area.
Vous allez tout droit, monsieur, la toxique arrive, alors circulez.
The ghosts of Europa had returned to haunt the tigers in the jungle.
Okay, so I can kill that video, I think, for now, and let's go back and take a look at the slides here. So what went wrong? Here's the big explanation as to what went wrong, but you pretty much saw it. The rocket turned sideways 90 degrees. Rather than have you read through all this stuff, here's a description. So, we had the rocket flying under flight control, and an inertial guidance system was directing its course. There were sensors in the rocket that were feeding information to the guidance control computer, and that was keeping the rocket on course. Unfortunately, keeping the rocket on course was the issue that caused it to blow up. The guidance control computers, there were actually two of them. There was redundancy here. If one of them failed, the other one would get it. they're responsible for keeping that rocket going. If one of them fails, it passes on control to the second. And that can happen. You don't know what might go on. So you have another computer of the same kind take over to do the analysis. In this case, both of them failed. And they sent an instruction, basically an error message, to the flight control in the rocket that the rocket didn't know how to interpret. And not knowing how to interpret it, it read it as best it could, and it read it as saying, I have to make a decision here. I've been given an instruction. The guidance system has shut down. I'll do the best I can. It looks to me like this thing says, turn 90 degrees. So it did. And now a rocket going up in the air at 90 degrees isn't stable, and the whole thing blew apart. What happened? What happened was that the European Space Agency built this rocket, which blew up and took $500 million payload with it. They built this rocket based on the specifications of another rocket, the Ariane 4. They never anticipated the problems that would happen with the guidance control unit, especially when the whole thing was lost. I mean, that just did not come up under anyone's radar because the Ariane 4 never had any such problems. It worked perfect. And that was really where things had gone wrong. When they designed the Ariane 5, they assumed that they could take everything from the Ariane 4 that worked perfectly and just move it over to the Ariane 5, to their new rocket. Unfortunately, the Ariane 4 used 16-bit integers to store its data, the velocity data. Now the sensors produce 64-bit doubles, and that data was being read into these 16-bit integers, and you can imagine what might happen. It turns out it's okay. The computer can compensate as long as the numbers are small. There were never any problems. But the Ariane 5 was faster, and so its velocity was faster, and all of a sudden the numbers coming from the 64-bit computers being sent to the 16-bit guidance control units were too large to fit. And as it tried to put a 64-bit number into a 16-bit integer, that's when the guidance control unit couldn't handle it, and it produced a fail state. And of course, it doesn't matter how many guidance computers you've got, they're all going to fail trying to do the same task, and so the rocket went off course and blew up. There are the sensors down in the lower right. They're producing 64-bit doubles. They're feeding it to the guidance control unit, which only has 16-bit integers to store data in. And so it just can't work. Here's a representation of both of those. You see in this long colored section at the bottom here what a floating point number looks like. That in this case would have generated the huge numbers coming from the sensor, 64-bit numbers. You've got one sign bit at the far end, and then you've got a portion of it, a number of bits that store the exponent, and another portion, all the pink bits that store the mantissa. So this is how floating point numbers are represented. At the top, on the right-hand side, you see a plain old integer, a 16-bit integer. You've got one bit designated for the sign bit, whether it's a positive or negative number, and all the other bits represent the data. And they can't possibly store what might come from this giant floating point number below. But that's what happened. So back a slide. When the 64-bit doubles got shoved into the 16-bit integers and proved to be way too large, basically the units couldn't handle it. They collapsed, produced an error state, handed control to the next unit, which also produced the error state, and the error message got passed on to flight control, and the thing blew up, all because of data types. They tried to put a large number into a small one. A floating point number, or in our case this would be a double, they tried to put a double into an int. So let that be a lesson. You can do some things. You can put small numbers into integers, but you can't put large numbers in. Normally, what we say is that you should never try to put data type that comes from a very large number of bits into another data type that has only a small number of bits. That's called demotion. You're trying to demote it, move it down the scale. And that's where you have problems, and that's where we have failures. Okay, so that's today's lesson. And the next couple of videos, we'll talk about this, and we'll do some additional things with data. So thanks.